Now I hope you, let me adjust a little bit, got used to this idea. D is a symbol, and this is the whole thing is one compound symbol, and we're using this multiplicative notation for operation. So we're creating algebra just like we did with x and y for numbers. So D and I is the first example, and we're going to add it together and multiply and stuff like that. Here's some simple example. If I have D plus D plus D, I hope you recognize this as a 3 operator added together. And if you think about the meaning, it's exactly 3 times the operator D. And same thing if you have 2 identity plus 3 identity operator, that's exactly 5 identity operator. So it behaves just like numbers. We've seen that before. This I behaves like multiplicative identity. If you multiply to the left or right, it becomes exactly D. I forgot to write it here, is equal to D. Now, next example, it's a little bit more complicated. This is probably the main deal about this part of the video. Now, 2D minus 3I, I don't think you understand what those are. That's exactly what that is, coming out of these. And this operator here, 2x, this is the exponential function, and this differential operator. So we do the differential operator first and then multiply 2x. And this is simply multiplying 3x to the given function. Subtract. So this is an operator, that's an operator. This is a linear operator made out of linear, and this is a linear operator. So we're about to multiply these both, multiply in quotation in operator algebra. So wrote it down there, 2d3i multiplied by 2xd minus 3x. This is really, we do this operator first to the function, then we got this resulting function and put it into this operator. That's what this really means. Now see what's happening in the next line. We are multiplying this one to the first term and the second term. That uses linear. Remember that when we multiply this operator to the first and the second term from the left, it requires linearity of this operator 2d minus 3i. So we're multiplying this one 2xd, and we have to multiply that one to 3xi on the left as well. So there, it's 2d minus 3i is 3xi and multiplied on the left, and you can pull this one outside like that. It's because it's a constant. Let's look at what I'm doing in the next line. I first look at this first term. I'm going to multiply on this right factor on the right to each of them. Is distribution law. If you distribute from the right, you don't need linearity, but it is linear, but you don't need linearity to do that. So it's multiplied on the right, and this is multiplied on the right of this second operator. Since I is the identity operator, when you multiply this operator to I, they just become 2xd. That's why you see 3 times 2xd and I disappears. But you see 2xd written to the right of this operator 2d. So let's do the same thing here. So multiplying this 3xi to the right of this 2d, so that's what you see here. And when you multiply this one to that, I cancels, it just disappears, and 3 times 3 to the x. Or better known as 3 to the x plus 1, I, it's identity operator. So that's how it unfolds if you use distribution law back and forth, and this is how it unfolds. Same as the distribution law of numbers, but how these things unfold is a little bit interesting. So that's the next part. Okay, so how is this a d and 2xd is going to unfold? Is that this product rule. So I'm showing you the product rule here again. The version here is with d, but think about we're differentiating px times some function that is going to be the input of this operator. And here, instead of function, is a derivative of this function. But the way this is going to operate on the product of these two things is, this is not a composition, this is a real composition, this is really the product, it's a product rule. So d is acting on 2x, so that's going to be 2x times ln 2. Then plus the product rule, the second part is differentiated. So d is becoming d squared. dd is exactly the second derivative. And this part is as simple as it gets. On the right, we have an operator. On the left, function multiplied. This is the form that we wanted to keep. So I'm showing that part over here. And this is another product rule applied here. So I want you to pause the video and do this operator algebra using the product rule yourself. Okay, so if you do this operator to 3x, is 3x times ln 3, and the other operator stays there. And d is going to affect the second part, the factor here, which is I. So di, it's just simply d. So that part is simplified as in this way. So here, operator on the left, the function multiplied, operator on the left, the function multiplied. This is the form we want to keep. So the last part is function multiplied on the left to our operator. So that's simple as it gets. So we have this. So what I'm going to do is that collect the same thing that is on the right. So d is on the right, and d is on the right, and d is on the right. We're going to collect them. D squared is the only thing here. So here it is. There were 3 terms with a d on the right, so you can factor out like this. And d squared and I are the single terms with those factors. Actually, no, I has this one. There's another term that with I in it. So these simplifies to this part right here. So again, this d squared operator and d and I, these operators are on the right. So it's kind of easier. You go through the operator first, and simply after that you just multiply this function and operator, go through operator first and simply multiplied, go through this operator and simply multiply this function. So that's how we reorganize this function. Let me show you the original operator, which is the written one that is written down here. You first go through this operator and go through that operator, and operator can be just organized in this way. That's exactly the same operator, identically same operator. So this algebra becomes a little bit more complicated than just a quadratic expression of numbers. So that's this is differential algebra. More general is operator algebra.